Welcome back. Today we are going to be learning about acids and bases and how we do solution stoichiometry with acid-base neutralization reactions. For our grade 11 course, we're going to focus on the Arrhenius definition of acids and bases. So an acid must contain a hydrogen atom, which in solution will become a hydrogen ion. Okay, so an H plus ion. So our general equation for what an acid looks like when you dissolve it in water would be HA, where A represents any acid. So we'll look at a couple specific examples in a second. But you basically have to have a hydrogen atom attached to something else. And when you put it in water, they dissociate, okay? So they're going to be broken up into their ions like we did with our net ionic equations, into an H plus and an A minus ion. Now your anion, like I said at the beginning, A could be any variety of things. So an example of this would be if we take hydrochloric acid, so HCl, we put this in water, it's going to give us H plus and Cl minus as our two ions. Or another example, if we look at acetic acid, which is the type of acid that's in vinegar. So HCH3COO, so that's our acetate ion with a hydrogen stuck to it. When we put it in water, this hydrogen is going to fall off and give us a hydrogen ion and an acetate ion. Now I like to write the polyatomic ion acetate like this because what it actually looks like is a carbon with 3 hydrogens stuck to it, so that's CH3, and then it's attached to another carbon which has 2 oxygens on it. So it's double bonded to one oxygen and single bonded to the other oxygen, and this little negative symbol is actually on that other oxygen because it's gained an electron to have a full octet. So in the acid form, your hydrogen would go on the end of the oxygen there, if you remember your Lewis dot diagrams stuff. And then when we put it in solution, this bond breaks and we get an O minus and an H plus. Okay, so there's our general definition of an acid. It contains a hydrogen. When we put it in water, it produces an H plus ion. Similarly, okay, rather than a hydrogen, a base must contain hydroxide. So it has to contain OH somewhere, okay, and produce a hydroxide ion in water. So an OH minus ion. Our general equation for all bases, where B could be any variety of bases, would be BOH, so where you have something with an OH stuck to it, and when you put it in water, it dissociates to form a positive cation of B of some kind, and a hydroxide ion, so an OH minus. So a couple examples here would be if we look at magnesium hydroxide, so MgOH subscript 2. If we put that in water, that would break apart into Mg2 plus and 2 OH minus ions. Or another example, if we look at lithium hydroxide, LiOH, if we put that in water, it would dissociate to form a lithium ion, Li plus, and an OH minus hydroxide ion. So looking at comparing these two, acids produce H plus when they're dissolved in water. Bases produce OH minus when they're dissolved in water. Now the next topic we're going to talk about with respect to acids and bases is the idea of strength versus concentration. This is a very, very common misconception that strength means concentration, but they're two different things. So we're going to use this little chart and draw some pictures to help us understand what the difference between strength and concentration is. So strength, okay, is a measure of how much a particular molecule will dissociate in water. Now, dissociation is this idea of it breaking down into ions. That's what dissociate means. So strength is how much it dissociates in water. Okay, versus concentration is the amount of something in water. So that's like your moles per liter, like we've been doing this whole unit, that idea. So to help us measure this out, this top row is going to be written as high concentration, and the bottom row will be low concentration. Whoops. There we go. Then we'll also look at strong versus weak acids and bases. So on the left side here will be strong, and on the right side will be weak. So if we follow these two over, this box will contain something that is strong and a high concentration, versus the box below it will be strong but a low concentration. Over here, we'll have weak and a high concentration. And down here, we'll have weak and a low concentration. So we're going to use the example of an acid, and the acid that we're going to use is hydrochloric acid as our example. So here, example is hydrochloric acid, so HCl. Hydrochloric acid. Now this is a strong acid. Okay, so this is going to be our strong acid example. Versus hydrofluoric acid, so HF, is a weak acid. And I'll talk about what that means, hydrofluoric acid is going to be our weak example. So a strong acid with a high concentration, strong means it will dissociate completely in water. Okay, so strong dissociates completely or almost completely. So a high concentration means there's going to be a lot of it floating around. So we're going to have a lot of H pluses and Cl minuses because they're all going to break apart. We're going to notice that there's a lot kicking around. We want to have an equal number of H pluses and Cl minuses because there's 1 for 1, so we want to maintain the correct ratio. So you'll see there's lots and lots, and the box is very full, versus something that's a strong acid and a low concentration. It's still going to be dissociated, but there's going to be a lot fewer hanging around in a specific area. So a high concentration versus a low concentration. Okay, but they're both strong because they're dissociating completely in water. Versus weak acids or bases. Our example here is hydrofluoric acid. Okay, mostly will only dissociate a very small amount in water. Okay, so only dissociate a small amount. You'll get into a little bit more detail into all of this in grade 12 chemistry, but this is a good little preview. So a high concentration of a weak acid means we'll have lots of it, but most of it will still be stuck together rather than breaking apart into ions. So we're going to have a lot of HF molecules still stuck together in our solution, and only a couple will have dissociated into ions. Versus a low concentration of a weak acid, we're going to have mostly still it as a molecule, and just a very small amount will actually break apart. But low concentration versus high, less and more. So now looking at the strength piece, see how in a strong acid almost everything, if not everything, will be dissociated, okay, and all ions, versus a weak, a lot of it is left as a molecule and only a small amount have dissociated. Okay, so that's your difference between strength and concentration of acids and bases. So bases work exactly the same way, except for you'd end up with an OH instead of an H ion. So the pH scale is a way that we can use to measure how acidic or basic any solution is. So the pH scale is used to describe the acidity or basicity of a solution. Okay, this scale is logarithmic. Okay, which means that a solution with a pH of 2 is 100 times more acidic than a solution with a pH of 4. Okay, so it's not 2 times more acidic, it's 100 times more acidic. Every step that you take on the scale is 100 times greater. So let's try this practice question. It says, how much more basic is potassium hydroxide, KOH, than pure water? So let's identify here is pure water at 7. And potassium hydroxide is down here at 13. So how much more basic is it? Let's count the steps. So we've got 1, 2, 3, 4, 5, 6 steps on the logarithmic scale. Sorry about that. And every time you take a step, it's 100 times more basic. So each step is 100 times more. So therefore, potassium hydroxide is going to be 10 to the power of 6. So 1, 2, 3, 4, 5, 6, 10 times 10, 6 times, which is 1,000,000 times more basic than water. Okay, so this diagram, you can take a bit more of a look at it. It has a lot of common substances on it. So you've got milk, you've got pH of blood, you've got orange juice, you've got lemon juice, all kinds of different things, lime water, all over the place here. And so if you want to sort of check and see, compare a few things, we'll talk about this a bit more in our Zoom class. You can take a quick look here and see if you can maybe identify, you know, how much more acidic is lemon juice than milk or something like that, and give it a try yourself. Okay, here's a good chance to take a quick break before you move on to the next step. If you feel like you need to pause the video and take a little stretch or go outside for 5 minutes, this is a great time to do it. And then we have one last piece of stuff to go over on acid and base calculations. All right. So whether you decided to take a break or not, here we go into the last little piece here. This will probably take us maybe 6 minutes or so. So acids and bases react in what are called neutralization reactions. Now, these are a special type of double displacement reactions. Now, double displacement reactions are a lot of what we've been looking at in our solutions unit. So it works exactly the same way, with the sort of special piece being that you always have to have an acid reacting with the base, and you're always going to produce water and some other salt compound as your products. And a titration, so an acid-base titration, is a special lab technique that we use to determine an unknown concentration of an acid or a base. We're going to be doing an example of one of these in a lab after this lesson, so you'll get to see kind of what that actually looks like in a lab situation and what the technique is. So a titration is when a solution of accurately known concentration is added to another solution of unknown concentration. Okay, until the chemical reaction between the two is complete. So what you're going to be doing is you'll have an amount of a known concentration. This is an example. It doesn't have to be in the burette. They can be either way, but just as sort of an example. And you're going to slowly add it to a flask, perhaps containing something that has an unknown concentration. Okay, so you're going to be mixing those two solutions together, and once it's completely neutralized, you can determine the concentration of the unknown solution. Okay, so the volume of known solution used helps us to determine the concentration of the unknown solution. An indicator is used to show when a reaction is complete. So we've used a few indicators before in the past. You'll probably recognize phenolphthalein or bromothymol blue as ones that we've used regularly. And they change color based on whether it's an acidic or basic environment. So an indicator is used to show when the reaction is complete. It does this by turning different colors based on the pH of the solution. The point when the reaction is complete is called the end point. And equivalence point. So I'm going to define what those two pieces are. Equivalence point. Now, ideally, you want these two things, they are different things, but you want them to happen at exactly the same time in an ideal world. So you'd pick a specific indicator to do what you'd like it to do. So the endpoint specifically, okay, is when you actually see the color change. So this is when the color changes. Versus the equivalence point is the true definition of when your moles of acid are equal to your moles of base. So when moles of acid and base are stoichiometrically, it's a mouthful, stoichiometrically equivalent. Okay, so you'll have to look at the balanced reaction. To check out if it's a 1-to-1 or a 2-to-1 mole ratio, whatever it might be. So an example of a type of calculation you do with a titration, I have some sort of fake lab data here, and we'll go through how to answer one of these types of questions. So here, we're going to do a titration of calcium hydroxide by nitric acid. So the volume of calcium hydroxide is 5 milliliters, We know the concentration of the acid, and what we don't know is the concentration of our base. So we answer this the same way we would normally answer any kind of stoichiometry question. So we'll go through the steps of balance, moles, ratio, convert. But before we start that, we have some lab data to finish dealing with here, and that is when you do a titration, you have your solution in what's called a burette, and it has a whole bunch of graduations along the sides. And it will be full to a specific volume, and you'd read that volume. So this would be your volume initial. And then as you add to your flask at the bottom, okay, this volume is going to be expended and it's going to go down. And then you'll have a final volume that you'll read at the end. And the amount that you actually used to neutralize your acid or your base or whatever down there is going to be the difference between these two measurements. So this is actually the volume measurement that we really want. So to do that, we have a few trials here. So you always do a titration, ideally at least 3 times, because there's little errors that can happen and we want to get the most accurate measurement that we can. So here we have 3 trials, and we want to find the volume of nitric acid that was used to neutralize this calcium hydroxide for each trial. And then we're going to take an average to try and mitigate as much error as we can. So trial number 1, we had an initial burette reading of 0 milliliters. So it was right at the very, very top. And after our first titration, we read a final reading of 8.62 milliliters. So that means we used exactly 8.62 milliliters total for trial number 1. Trial number 2, we're starting at that 8.62 milliliter mark. So that's our initial reading. After we've expended some of our acid into the volumetric flask, we take a second reading and we're at 17.35 milliliters. So the difference between those two will be the amount that we used the second time, which is 8.73 milliliters. And trial number 3, again, we're starting at 17.35. We do the titration. At the end, we read 26.03. That's going to give us 8.68 milliliters. So now, step number 1, okay, is calculate the average. So calculate average volume of acid added. So we do a normal average calculation. We're going to add them all up. So 8.62 milliliters for trial 1, plus 8.73 milliliters for trial 2, plus 8.68 milliliters for trial 3. We're going to divide that by 3 to get an average volume of 8.68 milliliters. Okay, so this is our volume of HNO3 that we're going to use for our stoichiometric calculation. So now it's just kind of a regular stoichiometry question now that we have all that information. So let's set it up the same way that we always do. First step is balanced reaction equation. So our reaction equation is between calcium hydroxide and nitric acid. Calcium hydroxide, CaOH2, aqueous, plus HNO3, which is also aqueous. It's a double displacement reaction. Our H and OH are going to pair up to form water, and then we're going to get calcium nitrate as our other piece. So CaNO3, 2, and nitrates are always aqueous, plus water, H2O, or you can write it as HOH if that makes it easier for you to see, and water is a pure liquid. We need to balance this, so on this side we have only 1 nitrate group. Over here we have 2 nitrate groups, so we're going to need a 2 in front of our nitric acid to get 2 nitrates. Okay, and then that gives us we have 2 hydrogens here, and over here we have 2 hydrogens and 2 oxygens, so that's going to give us a total of 2 water molecules because we have 2 oxygens and 4 hydrogens on this side, so 2 oxygens and 4 hydrogens on this side. So there's step number 1, our balanced reaction equation. Now it's helpful to organize what we know. We know our volume of calcium hydroxide was 5 milliliters. So V equals 5 milliliters, which we want to convert into liters always, which will be 0.00500 milliliters. And the concentration of this is what we don't know, and that's what we're looking to find. Now our nitric acid, we know the concentration of our nitric acid, and we know the volume of our nitric acid. So volume for this one is 8.68 milliliters, which in liters will be 0.00868 liters. And our concentration of our nitric acid was this 0.586 moles per liter. So now that we have our information organized, we can continue on through our regular steps of stoichiometry to find moles of, this is kind of our, if you think about our note from last class, this is A, and then this is B. If we want to think about it like that. So we know all this information about A, we want to find the concentration of our compound B. So we'll start with our volume here. We want to find moles of A, so we take our volume and we're going to divide it by our, or multiply it, pardon me, by our concentration to get moles. So 0.00868 liters of A times 1 liter, and moles on the top, moles of A, which is 0.586 moles per 1 liter. Liters divided by liters will cancel each other out. So that's our moles step. Then we have our ratio step, where we want to convert from moles of A, because A, so A on the bottom. We want to find moles of B on the top. This is a 2-to-1 ratio. So the 2 here comes from the 2 in front of the nitric acid there, and then a 1 for our calcium hydroxide. Moles divided by moles cancel each other out. And this, at this point, we're going to need to actually do the calculation and find out our moles. So we take 0.00868. We're going to multiply it by 0.586, divide it by 2, and that will give us 0.002543. Now I'm keeping an extra number there. I'm not going to round until the very end of the question. So that gives us moles of our base, and we want to find concentration. So C equals N over V is our equation. C of our base is equal to our moles of base, which was 0.002543 moles from there, divided by the volume, and the volume that we found or that we were given at the beginning was that 5 milliliters. So 0.00500 liters. Okay, we found that earlier. That should just be liters. Get rid of that. There we go. And that will give us a concentration of 0.5086 moles per liter. We get to keep 3 significant figures in this question, so that's going to give us 0.509 moles per liter of calcium hydroxide. We want to finish this off with a therefore statement, so therefore the concentration of the calcium hydroxide solution is 0.509 moles per liter. So hopefully you recognize that the actual stoichiometry piece is exactly the same as any other stoichiometry question. The only part we've really added is this sort of dealing with data step. So where you're given data in the form of like lab results, and you have to kind of figure out what that all means and find an average before you can actually begin doing the rest of the calculation.